but let's get started for lecture 5. And I hope the homework was, you all enjoyed the homework as well. So basically today we'll start to continue and start going further from what we have been doing in the course. But just as a refresher of in homework 1, the first two problems that you saw in homework 1 are pretty much about what are the relationships, Fourier law, and how we can take gradients of temperature or concentration and get flux relationships. The second part was conservation equation is that we derived on a control volume, we did a balance, and we got conservation equations. And then the third part was boundary conditions like constant value, constant flux, interfacial balance. Okay. So there were two kinds of 1D study problems that we have done till now in class, and then I'll also mention the one that is in homework. So we did the first problem we did was A going to B with a rate constant PV. Is the first problem we did in the class, where like this, and it was a 1D study problem. So we just pseudo binary system where two components are dissolved in a liquid. The second problem we did was a binary gas diffusion problem where we had y equal to 0, y equal to L, and we had A going to 2B. Okay, so in your homework, you did A going to MB, and in your homework, you did it in two ways. Show how you can use mass average velocity and a molar average velocity and get to the same point. So hopefully you saw at least one practical example where the formulation you can choose either or. You can choose molar velocity or mass average velocity, and you can get the same answer. Okay, so this is what we have been discussing till now. One thing I did forget to mention in the last class that I just want to emphasize again. So here it was A, B, and a surface reaction. And it's just so that you can start to think about how your transport would relate to some of the research that you might do. Something like this is very common in a calculated system. Okay, when you have a gas diffusion and then there's a heterogeneous gas. So transport of gases is very common in infections. Other one is x0, thanks. 0, and that's why my x is also that should be thanks. And a liquid phase reaction is actually can be important either if you're studying like organic system or something like that, or you may be interested in a biological system where you're thinking of a liquid phase reaction. That's where you think it's important. So just to give you an idea, all of these are simplistic systems. They're actually not that bad of a first starting point. So today we will discuss some problems where actually there was a paper that came out just 10 years back, and we'll discuss it today. It was also approximately 1D study problem, and they could answer all their questions. Okay, so while this looks simple, this looks obvious maybe sometimes, this is actually not that practical. Some systems can actually be reduced to 1D study problems, and that's where we'll go today. Okay. So just to kind of recap, so all of this is what we have done. So today what we start to do, and then this is going to carry through the rest of the part 1 before your exam 1, is actually focusing on how to use this flux relationships, conservation equations, and boundary. Okay. The simplest example is you will be given that the problem is 1D and state. In that case, you literally just have simply going to one-dimensional differential equation, one variable differential equation, and it's easy to solve. Now, what we'll do today is approximately 1D study problem. Okay, so today's agenda is approximately 1D study. So, what do we mean by approximately 1D study problems? Approximately 1D study problems are problems that can be reduced to 1D steady state, but are not inherently kind of given to us to be 1D study. And that's actually a very crucial point I want to emphasize, is that I have seen students when they are doing the PhD research, and if they have some sort of a transport component, they'll come and they'll just make the problem 3D, unsteady, have all the complications. But more often than not, you'll find that you can actually reduce the dimensionality of the problem and simplify it. And that's really the key component that you have to kind of take away from this course is how do we go from a more complex system and slowly boil it down to something that is simple, tractable, and then you can solve. Okay, you don't have to solve always the most full set of equations. So let's today discuss. So in the first part you saw, we just told you it's a 1D and steady system. Now we'll not say that. We'll show you how we can arrive and make it a 1D steady system. Okay, and slowly you start to kind of add to that. All right, so this is basically the goal. We are still in chapter 3 of Dean. So this was chapter 1 and 2. This is a recap, some students like to use the book. Chapter 3 of Dean is what we are still with chapter 3 of Dean. Approximately one is steady problem. And I personally prefer to run these examples now. So we have done enough problems, done enough derivations. So we start on a problem. So the first thing we focus on today is pin design. Okay. This is our first problem today. This is a heat transfer problem. So think of a solid wall which has solid material where we have basically added this sort of pin at the end. So the temperature here X, Y, we have kind of added a rectangular pin. Which we have added to a solid wall at temperature, solid sort of material at temperature PW. And we have been given, and as we discussed this, there is air outside, that is heat transfer coefficient is H, and we haven't defined it yet, so don't worry about what this heat transfer coefficient is. We discussed that. And this is the temperature of we are far away from it's everywhere. The temperature in air is the same, heat transfer coefficient is the same, all sides of this pin. And the goal is find X, Y. So basically, this is a 2D study problem. This is a 2D study problem. And what are we trying to do is our goal today is to think of approximately 1D study problem. So we really want to make this problem from 2D study to 1D study. And that's what I will focus on today, is how to go from something like a 2D study problem to a 1D study problem. And obviously, this is not going to happen all the time. We have been given that HW by K is much smaller. So all of these things will become clearer with time, but we're going to set up the problem. So think of a solid wall. If you like to visualize, think of something like iron sort of block, where you have a small rectangular pin coming out of this. There is a third dimension, but think of it as infinite. Okay? So we currently are not worried about the third dimension. The book actually has some discussions about the third dimension that I'm very curious, but we'll not discuss it today. So just think of a rectangular pin coming out of a solid block of metal, think iron or something like that, and then there is air outside. Okay, and we want to find a steady system. Heat transfer, heat is flowing through because it's a key wall, it's hot, and the air is cool. Okay, so the heat is flowing through. At steady state, there will be some temperature profile, and we want to find that. And the goal is, well, 2D problems, obviously, we need to solve more. We want to convert from 2D to 1D. If is it possible to convert into this? Okay? So that's the problem set. Now, before we go into the details of this, let's quickly discuss why this is kind of why would this be interesting? So this is kind of like, I believe many of you must have seen this. See, like the pin design is like a very important part in heat exchangers and I mean the design of engines. So what you see here is a 3D design of different engines, Yamaha design or different designs, and there are different kinds of them. This is again we are thinking about constant area. You can have variable area. There are many different kinds of design, and the main idea is you just increase the surface area so that you can cool it better. So that's the full field. Obviously, we are just like finding something very simplistic. But I mean, this is actually not the only application. One application that I also find was cool was what is the elephant here? So this was actually a paper that came out, I think, when it was about 10 years back. And what it did was it did a heat transfer problem on a cylindrical thing and kind of showed how to think of the optimal thickness of the elephant. And it is actually a heat transfer problem. Not very complicated. If you're interested, you can do it. It's a nice paper. And you experimental, gather experiments, and then they are trying to run more. So this sort of like simple sometimes analysis can give you the insights about very different problems. So I just find this, and obviously there are more complications, but just wanted to kind of motivate that there are other. So like this kind of heat transfer problems can also go beyond in design and think more about biological. All right. So with that, we'll start this problem. So I again, so now today, computer will be applying a lot of concepts into work. This is the problem setup. What is the first step? Governing equations. Okay. So just remember that whenever you see this, what is the first step? Governing equations. First step is governing. I should just mention one thing. What I forget is that the heat conductivity K is constant. You can almost always assume it to be constant, otherwise unless we take. So this is assume this to be constant. Governing equation. So what is the governing equation for heat transfer? It is del E by small del T plus E dot del T alpha del square T plus H. So any thoughts on the first term? What is happening to the first term? 0, perfect, great. Steady. So we can remove this. What about the second term? Why? So why is it no conversion? Yeah, you're all right. So why not conversion? I mean, you're all right because it's a solid block. It's not moving, right? Like it's a solid block. So in a fluid phase, it's a little different. A solid block has to move together have any velocity. Not moving. It's just static, right? So it's not moving. When we say convection, just remember that a solid system has a different meaning of it. It's a rigid body. Fluid may have a local velocity. This is zero because the solid is stationary. What about HV? Do we have any volumetric generation? No. By the way, this is also a good point to realize that sometimes students get confused. It's implicit that I'm writing this equation in the solid fin. Okay, this equation is only in solid fin. I'm not writing it anywhere else. Right now, this is only the solid fin. So I'm not writing in the air phase. In the air phase, there will be a separate equation, but they're not interested in solid. So essentially, our equation comes out to be alpha dash per t is 0, or simply that means del square t is 0, and it becomes del square t by del x square plus del square t by del y square. So that is my equation. It's a two-dimensional equation. It's a partial differential equation that we would like to solve if you want to solve the full problem. So this is the governing. Again, remember, I want to again emphasize, we want to come to this point when we are learning how to simplify governing. Start there, simplify to this. This looks good. All right, now next is boundary condition. So we haven't really done this till now, but how many boundary conditions should we expect? 4. Some of them said 4. Why? Does anybody want to just volunteer? Why 4? So the answer is 2 for x and 2 for y. And if some of you are confused, it's basically it's all right if you're not before. We have a second derivative in x and we have a second derivative in y. Okay? We'll have four boundary conditions. 2 in x, 2 in y. Another way to think about this is if some of you kind of don't see that, like more specifically is I have a rectangle. I'll have two boundaries in x and two boundaries in y. So it has to work out this way. So we have basically four boundaries and we want to get the answer in that. So we'll have four boundary conditions. Four boundary conditions. 2 in x, 2 in y. That's hopefully that's clear. What are the boundary conditions? So let's start with first in x. So what is the boundary here? What are the boundaries in x? Equal to 0 and x equal to l. Right? So that's starting with the end of the thing. So let's start with x equal to 0. So I think the value is given to us. It is simple that for 0, y. So for all y's at x is equal to 0, the value is 0. This is given to us. Now let's do boundary condition 2, which is the boundary condition at x equal to l. At this point, this is something we have not discussed in detail, so don't worry if you have not seen the transfer coefficient. So heat transfer coefficient is a way to quantify. So let's think of it like this. So in a way, this is telling you what is the boundary condition of flux boundary. So that is sort of implicit in that. And what it is really saying is that the flux coming through this x is equal to L surface. And so again, we have discussed several times now, but x is equal to L, the flux will only change the x, but the normal is perpendicular. Right? At this surface, the normal is equal to Ex. The flux will be only directly by direct. We have discussed this. So if my normal is this, what I will do is I take the temperature at the first point and then far away to infinity and multiply with x. If we do this a couple of times, it will become clearer. So let's say minus a divided by x is equal to h t minus t in h. Know that this temperature is also the temperature at equal to L comma 1. Okay, so this temperature is at equal to L comma 1. Why is the temperature same inside and outside? Should the temperature be same here and here? Inside and outside? Right? Because we said thermal equilibrium, right? Because at an interface, a temperature would be same, but not concentration. We'll do the concentration problem later down today. Concentration is the partition. The temperature would be same. So I'm actually using the temperature in the airplane, but it's the same as the soil because outside the molecule. This is how you write the flux. This was the question that came out last time, and actually one of the students asked me, and I never thought about it. Is why didn't I really take t minus? Why did I take t minus t infinity? Why not t infinity minus? Like, how do I decide this? So that goes from your direction of the normal. Okay. So because my normal is in this direction and is equal to ex, you can take the other normal direction again. The answer is but we have chosen this, so I'll take the temperature first at t and then at t. So I'll go in the direction of the normal. All right. So let's go further. So this was hopefully will become clearer. Let's keep going. So now we have two boundary conditions in x. Now let's go towards boundary conditions in y. So does anybody want to suggest the boundary in y? How do I go about it? What do I do? So good point, but we are writing right now. Range of domain. You're not even thinking about the airspace, right? So that's why I mentioned it's very common that my boundary is actually only the solid phase boundary. That's y to the w and y to the minus z. So, so because we're writing only in the part. So what you are asking is, how can I ignore convection? I cannot ignore convection in the real, but that's why I have heat transfer given to me. So that's why I'm not even good. Yeah, so in the third part of the course, we'll actually solve the AFC question. But right now, we are just kind of saying heat transfer coefficient is able to be applied. So that will include convection outside. But we are not interested in outside. We're only interested in the soil. Okay? So just want to clarify the boundary is y equal to plus W and minus. Okay. And again, what will be the heat transfer boundary? Okay, so what now send me a normal to the y to the field is plus y, right? And equal to plus y. So let's take this to the normal phase, normal direction. So then I'll say minus a del by del y is y equal to w equal to x t minus t infinity. Okay, so again note that I have taken this to be normal to the EY and I'm going from temperature T to T infinity far away. That was mentioned that temperature far away is T infinity, right? Because that's here. So T minus T. Now the interesting part is minus. What do you think I should take the normal? You can choose it to be arbitrary. Plus EY or minus? Let's take minus EY. Good. Let's take minus EY. And if you take minus EY, what will change? Will my I'll still go from T to T infinity, right? Because the surface is at temperature T, it is far away T infinity. So I'll write this and tell you if it is correct or not. Something is already said. Is it correct? Great. So just remember that because my normal is now negative EY, it will also be plus A delta T. Okay? It will be plus A delta T. Because normal is minus. So these are my four boundary conditions, and I now solve the problem. So how do I proceed? So now I have these four boundary conditions and I have the governing equation for the fourth. So we have this equation and four boundary conditions. So this is the full problem. If you just wanted to solve this problem with equal system, these are equations, boundary conditions, and governing equations, and you can solve. But we want to make it an approximately 1D study problem. So the question is, how do I go further from here? Let's go now here. So we have our governing equations, boundary conditions, and now we want to solve. But we want to convert it to 1D study. So what is the one thing that we want to exploit it now? We have exploited this here. We want to exploit this relationship. And where do I see this? How do I exploit it? And how do I go back? How do you think I plus boundary conditions, but which three plus boundary conditions? Which one? One. The y direction, so that we will see that because I am taking a derivative in the y direction, and my y direction is of the length w. The formula is hw by k. I see h here, I see k here, and the delta y is basically roughly on the scale of w. So this is basically something we'll do more again and again in the class. Order of magnitude analysis. Okay, so order of magnitude analysis is not trying to solve this boundary condition, but it's trying to kind of estimate what this tells us. So let's do this. So temperature, so delta T, let's imagine that temperature the center is denoted as T, and temperature at the end here is denoted as T naught, like that. Then delta T, so plus y to minus y is T naught minus Tc minus A delta T. Okay? And delta y is, so what I'm saying is I think the maximum temperature is the rod will be hotter in the center that we can expect. And then the temperature starts cooling because of the air. The hotter in the center, so I say the temperature is Tc, and then it is T naught at the. I'm assuming I don't know these values. T naught at the, T naught at the end, and then delta y is changing out W. So what I will do is I'll approximate. Go here and say minus k L T by del y is approximately minus k delta T by delta y. Dc minus T naught, so that the negative sign was becomes okay. What I've done is del T is just approximate. I'm not using the exact, I'm just approximating. Important to understand this is not a mathematics, it's just like trying to get a sense of the scale of the problem rather than solve it mathematically. Delta T is Tc minus T naught, like T naught minus Tc, but for the negative sign T naught, and delta y is the width of the system. And then this becomes equal to T minus T infinity is basically H T naught minus, right? Makes sense? So what we are saying really is minus K del T1 del Y. When you say this, so what I'm so K T minus T naught W H T naught or T naught it's not random that I decided to use a box condition. I use it because I could see that I need a width, and the width is delta y. Okay, so that's how we go from there. I want to emphasize this. Sometimes students say like, this is kind of you're just making this up. Like, how do I think about this? That I want to use the boundary condition is because x w by k comes clearly when I need a delta y. I need a delta y is what. So that's why I use boundary condition. Alternatively, we use boundary condition 4. So we get this. And what does this mean? So what does this, can anybody suggest? What does this ratio, how can I use it?
That means that like deviation of t from long direction is like
you're thinking along the right direction, but thinking along the right direction, I want to improve that further. So the suggestion was that the long direction speed is insignificant compared to the short direction. So what is T naught minus T infinity? T naught minus T infinity is the temperature from the wall to the air. Right, from the wall to the air. So it's really saying is that the temperature change in from T naught to T infinity is much bigger than from the center to the wall, right? So that means that my y direction temperature change is practically negative, right? That's the technique. So we will use this. This means is change in y direction. Okay. So this is what it is saying compared to what's happening outside. It's really just changing a little bit. So for instance, think of it like this: if my if I had and what okay, then let's go one step further. What do you think the TC can be? What do you think the maximum temperature in the center can be? TW, right? That's the hottest temperature can be TW. So or let's take it further. We're saying TW minus T naught minus T naught minus T infinity is much less than 1. So think of it like this: is that if my bar is at 100 degrees Celsius and T infinity is let's say 10 degrees Celsius, right? And the change that is happening over that y scale is much smaller than the what is happening in the air. So because of this because of this factor, basically this start not change we'll basically ignore the change in y direction, and we'll discuss this a little bit. Oh, so good question. So it's the interface temperature is T naught. So the temperature at interface, maybe here, the temperature at this is T naught. T wall is the temperature here. So that is not the air. This is not. So yeah. So yeah, good question. So why did I choose delta T to be T naught minus T, right? So that's because which is it's at a higher y. So delta T, I need the temperature first at the higher y value minus the one at the lower y. Right? When I take a derivative, I need to move from like T2 minus T1 by y to minus y. Let's do it. Del T by del y. T2 minus T1 by y. Okay? Does it make sense? Like I'm just saying, I'm trying to approximate delta T by delta y as difference is that some take some y1 become y2 and then temperature at that point and temperature at t2, right? So and let's take y1 to be 0, y2 to be less. Okay, then it becomes T temperature at y2 minus temperature at the wall is T naught minus T minus wall. There is another way to get to this. Del T by del y. And then the negative sign is automatic. So that is another way you can think about it. So you can go that way, or I mean, other way to think about this is also your flux. You know, the heat is transferring in the positive y direction, and it is cooling here. Then I want this temperature this value to be positive, and when it is positive, then because the temperature of the center is other than the temperature of the wall. So that's another. So you can always you can go about it either way. People for you know either of the options. It should all come out. Any other questions? All right, okay, so we do this. So now let's go back. This is what something we have used. All right, so now let's go to the problem. We have del square t by del x square, del square t by del y. We have the two boundary conditions in x and two boundary conditions in y. And we have been told that the change in y direction is relatively negligible. So what do I go about it? Should I just ignore the second term? Should I just drop out this one? Is that the implication of changing y direction? Does it mean that del square del y square is? Absolutely. As you see at this excellent point, this is not del t by del y. This is the most common mistake. When we go to get this, go to this point, like, yeah, we got this, and then the cross of this term. The second derivative and not the first derivative. Okay, so we'll come and use that in a second. But this is the point. So what do I do now? Like, how do I proceed further? The idea is that my y direction seems to be less important, right? Like that is clearly something is not as changing in the y direction. So we want to integrate that direction out. So that's the logic, is that because y temperature direction is negligible, we integrate in y from minus w. Okay, that's the idea. So let's go further. Del square t by del square dy. And I hope it's not because math course must understand this. You can also change the order. You write it like t dy, first integrate in y, and then take the derivatives. That is allowed. And actually, once you integrate in y, it become a d square by dx square, because now you have washed out the y dependence. So you become a derivative instead of partial derivative. And what is the d square del square t by del y? Del t by del y. This becomes plus Any questions on this? So I'm really, I want to, so some of these concepts I mentioned that this is kind of, we are making this up along, we are not really, how will I think about it? That's what I want to emphasize, is that it's not random. It is because we think that the direction in Y is not that important, we're kind of into it. So just kind of follow along the process and it will become clearer. I'm going to give more examples in a bit, but this is how the thing works. Do you have a question? Oh, zero to W, yeah, you can do that. Absolutely. Great question. The only reason we do that is because we use a boundary condition in both eyes. The other way to think about this is, and this is not a consideration, you can say argue symmetry. You can say there is symmetry around Y equal to 0. You are getting fixed the system with the same. In that case, the symmetry means that the derivative will balance Y equal to 0. That will be the result. Any other questions? Okay, so we do this, and the reason we do this is that because I know the value, right? Boundary condition. I know the value at del d by del y. Boundary condition here. I know that del d by del y at y equal to w is h into t minus t infinity by k, right? And this is h into t minus t infinity by k. And the other values. When I subtract this here, use boundary condition. I'll get t square by dx square minus w y. I'll get plus w of t minus t infinity. Okay, this is what we get. So I've just indicated in the y direction because it seems the same in the y direction. Less important, and then I've put in the combination to get the right answer. This is what we have done. Now, how do I go about this? So this is this idea again of y being less important. Is that I will define an average temperature. So you can see that this is PDY. I'm trying to wash out the y direction. So I will say, as by definition, I'll say this is something like average temperature times whatever. Okay, so I'll argue this. This is not something I already know. I'll argue this. This is P temp average temperature Fourier function of x times 2w because I can basically this. I'm not interested in the y direction. So finally, this becomes 2w d square dt by w square minus hw t minus t infinity by k at y equals w. So that's it. So how do I go further? Yes. Just the first. Because of the yes. Oh, bar is the average. So this was defined as average. Average. So am I stuck now? Like I want to solve the differential equation for an average, right? But then I have local temperature. I need at y to w and y to minus. So how do I? Yeah, so that's a great point. So that's a good question. So these two values should be the same. So we can add them and become twice. But let's take a step back. Let's not go there yet. But what do you think about like how do I prove for this? This is a local temperature and this is an average temperature. So I'm stuck. What do I do now? So what do we know about the system? So this is not a intuitive problem, right? So that's why I'm trying to kind of build it up slowly. It's from 2D study to 1D study. We are going closer. We are getting to T bar 1D, but we think that is fully dependent of some temperature at Y I do not know. The point is, the whole exercise is hinged around this idea that the change in y is negligible. So would you agree that the average temperature is equal to the local temperature because the change in y is negligible? So I can approximate the temperature at the walls to be the same as the average temperature. So that was the whole idea of using orthogonal analysis, is that when you integrate out the y direction, you will get some boundary condition in here locally, but this basically the average value is the same as the local value, right? So that's why I can say that P, so that here the reason I'm saying that P x comma y to the w is actually equal to P bar. This is my approximation. And P at x comma minus w is also equal to P bar. So this is the whole point. Yes, please. Oh, actually, you're right. H by W here. Thanks, Rajesh. I think I made a mistake here. It should be, sorry, actually, so there should be no, there should be no. Thanks. That was my mistake. Get out. So there is no, I this is the time. You will see in the boundary condition, there is, but I, by mistake, any other, but does everybody see the point? HW by K told us that the change in y direction is negligible. And so we can say average is the same everywhere. So it's just not changing in the y direction. So when you do that, again you get equation. You can sum it up and you will get d squared P by dx squared is h by w k d bar. This is the equation. There's the final governing equation which is reduced from two-dimensional. That is P bar. And we have gone from 2D study to 1D study. And I'll discuss the boundary condition in a second, but this is essentially the whole point. So let's recap. We have done a few things right now. Let's recap. So we started the problem with saying we have a rod study, we wrote the governing equations, simple, that we did, and the boundary conditions. Hopefully that I introduced the idea of another position. That was simple. This is the part that's supposed to be specified on how did we come up by this order-minded analysis. Again, I want to emphasize that this is not something that we use. First, it was given in the problem that this is much less than one. But more importantly, see that the boundary condition kind of shows you can use that boundary condition to kind of inform something about the system. When we use the boundary condition and do orthogonal analysis, we learn that the change in y direction is negligible for temperature, and that's why we integrate in the y direction and use that the average is equal to the local temperature. Yes.
In this derivation, like, could we also have put it to define our coordinate system starting from like y equals 0, and then like solve it that way, and then instead of having one of the, or instead of having the boundary condition that I think the boundary to like some condition.
Right. Yeah. Absolutely. That's what that was. If you symmetry according to 0, you get the same answer. Yeah, absolutely. That's allowed. Great, excellent question. I'm glad somebody asked. So the question, the comment is, didn't you assume this number was more than one? So if you just go to 0, did you assume this is more than one? We assume it to be HW by K to be much smaller than one. Okay. So what happens is, great question. I'm really glad you asked this question. Is d squared is bar. You can think of it like this. This will become 1 by W square, right? And P bar minus T infinity. Okay. And so now, if you're doing a scaling analysis, you see there is also an x square here. So that's the length square, and this is in the x direction. So it will be L square by W square times h divided. And if the length is much bigger than the W, which is generally 2 strings, then this value cannot be much. Great question. This cannot be much. This is much more than 1. But you can do an order of magnitude analysis. Let's do this because it's a great question. delta x is actually L. So this will mean that this delta t bar will be t bar of some value of 1. Then I'll say Tw minus T1, but T1 minus T1 T will come out to be by T, then L by W. Because this is square, so that's how the square comes in. And the square is always delta T. So we haven't covered this, but I just want to, because it's asked. Remember that we can delta for a second derivative in the numerator, but for a second derivative in the denominator, we use a square. That's how you kind of see the difference. And when you do that, this value saves at the end. If this was also 1, then you will not have great question. Does that make sense? So you get this value 1D problem and then you get the answer. You can solve the answer if you have the boundary. Let's say a quick poll, we haven't done that yet. There's a quick poll on what do you think would be the boundary conditions. Hopefully this is straightforward. Let's do a quick poll and see what do you think are the boundary conditions for this problem. Then further from there. So and now let's see, let's say just another 5 seconds or so. Let's wrap around minute 1. To participate, we're going to get a sense of the how to look at boundary conditions. Look at your boundary conditions. So, sorry, I should have mentioned thanks to this not in that might have forgotten to change. Sorry, not sometimes use let's take another maybe 5 seconds. Stop it now. So most of you say C, some say B. So does anybody want to explain the choice? Why B or C? There is nobody in A. B or C. So the confusion whether should be no flux or that, right? So let's go towards our boundary condition. And so our boundary condition is here, right? Second boundary condition is here. And we have learned that any y dependence is not interesting. So I can simply say that T is equal to T bar. Right? So this replace T is T bar. So that's why the answer is C when you have the boundary condition. So I'll just write that here. T bar 0 W and minus dt bar L. You can solve this problem. I will not go into details of how to solve this, but this is solvable. It's a solution. So again, my emphasis is not on the mathematical tip of solving this. My emphasis is making sure you're able to follow of how we were able to reduce it and get the right boundary. So governing equations, boundary conditions. You start with 2D problem. You use the scaling analysis of a getting more than 1. To remove the y dependency, we integrated it out, average it, and the average to the local one, and get it. Okay. Before I give a quick break, let me just emphasize that this is not, this looks like, okay, can I ever use this? It's actually a very highly cited paper. This is saying evolution of glucose profile surgery system of stem cells. So some of you are interested in biological application. This problem, it was solved exactly like this. This is the paper from 2006, yes. And again, very important paper, check it out. So instead of it plus, there was a chemical reaction on the cells of oxygen, and there was a zero order reaction. There was a constant organism. And actually, I have a supplementary video which I upload today, which talks about how we can use what we learned in the class to solve this problem. So they started with the 3D boundary condition. With 3D system, they said, well, we can ignore one dimension to become a 2D problem, and they used a similar analysis to convert it to 1D study and use the same equations to solve it. So again, I'm just trying to emphasize that you can look at the system and want to solve 3D and study or something like that. But it's not required always. It's about using these assumptions. So I have a video which kind of goes into this, and this was also solved in the book. If somebody is interested, you can take a look at the book. The book actually gives out. So let's right now it's 9:21. Let's start at 9:25. So we'll have another 15 minutes after that. Let's take a 4-minute break. Start at 9:25 and do another problem. It won't be right because good questions. I think you're asking the right questions. Steady state does not necessarily mean that the temperature is the same. It means that the flux is constant. And a flux is constant can have a lot. I think that's what I'm trying to say. So the temperature, you can ignore maybe data for response. Then you can ignore the temperature gradient in the direction. Yeah. But the reaction even at equilibrium, that doesn't mean it just means that it's not changing with time. That can change state. Because some heaters have heated this hot, right? You always put it. It's always yeah, if I say this, the last if I don't impose, then we have to use higher. But default active, oh yeah. So what I was trying to say was what is the highest that can happen? PW. Yeah, that is the highest. That is the argue that when I'm trying to compare here, much higher than here. Oh no, no. This is my definition. All I'm saying is only one part is equal to this. All right, let's get started again. All right, let's get started. We have another part covered. So the second problem we'll cover today is evaporation of a liquid column. So let's start here. Y equal to 0, y equal to e. Is okay. Gas to liquid phase. A represents air. B represents organic vapor, and liquid is pure liquid. Some of you may have done this in undergrad. Some undergrad have this acetone evaporating experiment, but maybe not. What we are really doing is think of a liquid column of acetone. This is done in lab all the time. Or at least used to be done in lab. You will take a column, the tall column of acetone, and leave it in air, right? And with time, basically wrap acetone is organic liquid. And why is this kind of interesting is that this problem is actually is interesting because even though this again looks like a simple problem, it actually informs design from emissions from organic tanks. Nowadays, increasingly important in terms of environmental regulations such as very strict control on design, right? So if you have an open tank, which is organic liquid, and evaporating, it can inform how much emissions are coming out of it. So again, looks like a simple problem, very important. These evaporation rates are very important to understand in oil fields. Obviously, oil fields don't be like a liquid column, but it can be some understanding of how many evaporation rates in an oil column. And very traditionally, this method is used to measure efficiency. So, organic liquid, so for instance, like I was saying, is actually measured for traditional or just classical. So the problem really is this. The problem is that this is a 1D unsteady problem. We have a liquid column that is evaporating. Okay, so it's evaporating with time. All the liquid will go out, will all merge into the phase. To simplify, in a natural system, any air will have oxygen, nitrogen, methane, carbon dioxide. We'll say we'll forget all of that. We'll say air is A. This component A. It can have multiple components inside. We'll not worry about it. We'll just say component A is air. It has all other gases, and B is the organic vapor of acetone. Okay? This is a binary gas. Again, just to make life easy, to say organic vapor of acetone is air. So there is a gas phase on top, and on the top at y equal to 0, I basically get here I get A is equal to C naught. Let's say C equal to C. Cv is equal to 0. You will see at the top of the column there is no acetone because my ambient air does not really have any appreciable concentration of acetone, and basically I just have here. And this is again isobaric, isothermal. So I go from a homework problem and the last discussion you can appreciate that Ca plus Cv is equal to C is equal to constant. Okay. When total concentration is constant, C plus C. So total concentration is constant here, binary gas excretion here, but this interface is moving down. And this is pure liquid. So the concentration of this is Cl. So some liquid concentration Cl, some pure liquid, pure acid. Now it is evaporating. Clearly it's a 1D unsteady column, right? Changing with time. The height h changing with time, and the column height is xl. So the question is, how do I solve this? Okay? So this is called a pseudo steady assumption. If you want to make it a steady problem, 1D unsteady problem. And we need make it 1D steady to pseudo steady assumption. Pseudo steady. So this is a study. This is the assumption we make that this is a pseudo steady. So before I proceed further, Can someone tell me what is the concentration of organic paper plus the water liquid? Partition. Great. So this will be some partition coefficient here. So value will be some partition coefficient times CL. But for simplicity, I'll just refer to the CV naught. But as I also currently find out, it will be some partition coefficient times. Okay, this is what I was trying to say, that when you have a gas species problem, there is a partition coefficient. When you have temperature, temperature is equal. Temperature doesn't change across. Right. Now, seriously assumption. So what is this seriously assumption? So we will prove this. I don't think we'll have enough time today. I take another 15 minutes of class, but seriously assumption says that as my liquid is evaporating, at each instant, my diffusion problem is fixed. Okay, so what is happening? Think of it like this. Think this is a 15 centimeter cord. Okay, 15 centimeter acetone. When it goes to 14 centimeter, I will have a new diffusion profile. Because my H has changed, so obviously the region has changed, so I'll have a new profile. But as soon as it goes from 14 to 15, again I'll have a new. At each instant when the acetone is evaporating, the diffusion profile is always set. It is not changing. Diffusion profile develops on the order of few seconds, whereas the acetone is an hour. Okay, that's saying that my diffusion problem is very fast and my evaporation is very fast. Okay? And I will convince you, maybe not today, but by the end of this class, of how this is a solution. Show that. Okay. The problem is diffusion is much faster than evaporation. That's the assumption. Diffusion is much faster than evaporation. The assumption is diffusion in gas phase is much faster than evaporation. That is the assumption, and we will prove that later. So at each instant in time, so whenever I assume steady, because diffusion is so fast, so I don't have to worry about concentration profile changing in time. I just have to worry about H changing in time. I don't have to worry about concentration profile. At each, whenever I have at each instant, I can assume H to be some sort of constant value and just evaluate it. Okay, so it will become clearer as we go today, but this is essentially the assumption. So with that assumption, let's start with our governing. So what is my governing? Governing equation, and now we are interested in the gas phase. Gas phase. Then I'm not interested in what will happen by the way in liquid phase, right? Is there any concentration? No, it's so liquid, right? Yes, I mean, that's the concentration power. So liquid. There is no concentration. But in the gas phase, at top we know it is C and C equal to 0, and at the end it's CV naught. So the gas phase. So what is the governing equation? Should I go to my conservation equation and look at the species problem? What is my governing equation? Anyone? That's a good point. Can anybody agree or disagree? So when can we use the fifth second law? The binary and the binary and is it the binary problem? The gas phase? No, that problem is solving the purpose. The gases problem of P comma B. We cannot use the usual 6-second law. It's not a pseudo binary constant problem. We cannot go to the 6-second law. What we have to use is the basic equation, which is that we say del B by del B, del B by del B, del del dot S, is equal to not pseudo binary. So now this Okay, so G can be CA, in which case F would be NA, right? Or B can be CE, in which case F would be N. Okay. There's some confusion last time, I want to emphasize. This equation is general, right? The first equation is general. I just can change my scalar and my fluxes, and I can get it. So is there a del B by del T term? No, right? There is no term because we are doing this zero study. If I did make that assumption, yes, there is something like that. There will be two zero studies, I can remove that term. Is there any generation? Volumetric? No. There is no volumetric reaction or volumetric generation of acetone or air, right? So that's correct. So I get del dot F is zero, and it's a 1D problem, so I get E N A Y by dy is zero. And B C A and E N by dy. These are my governing equations. The name exact, I hope you all see the just somebody like the same as the whole problem, right? Flux is constant also. The derivative of flux by 0, dn is derivative. Now boundary condition. So anybody want to suggest the boundary condition? So what are the boundary conditions at y equal to 0? Boundary conditions are given, right? We are given the one. So at CA at y equal to 0, right? And what is the boundary condition at the at y equal to h? Sorry, such condition. We should think of another great. So both are correct. So basically, we can use the concentration. We know the concentration, right? We know the concentration of B A here is. We know the concentration of B, right? Equal to 5 of B naught, and we know the concentration of A will be this C minus because CB has to be constant, right? So and CB naught is related to the partition group. I'm just not writing partition group. So I have this as the I can just solve it. Right? I have to bound the conditions and can I just solve it the problem or do I not have enough information? So now this becomes any y this becomes any y equal to constant and this becomes any y equal to right. This is what my governing equations are, right? I can integrate that any y is constant, any y is constant, and I have two boundary conditions. So should I do this problem? Oh, so yeah, good question. So basically, remember that the NA, right? NA is a flux which also has a second derivative of CA, have a derivative of CA. So it has second derivative of CA. So that's why I need two boundary conditions A and two boundary. That's a good question. So the think of it like that. Typically, when you have a boundary, again, you can see physically there are two boundaries. So you need two boundaries in both A and B. Yeah, good question. We're going there. You have to be going there. We're going to that point. So big observation. So NAY is constant, NY is constant. That was the next point. We can't solve anything right now, right? Because last time, you remember when we had a problem, we knew the flux because of a surface reaction. I just know it's constant and I know the concentration. So what I have not realized till now is that so I need to do that interface boundary condition because I don't have enough information about the fluxes right now. Okay? Okay, so this is what Noah was saying. So we need to use interfacial boundary condition. Interfacial boundary condition. The boundary condition is y equal to h of t. In the gas phase, the liquid phase, 1, 2, n is equal to y, and I will also make the velocity v. This is what I was saying, that we should expect now, because it is actually moving, right? It is actually moving. It's no longer constant, no longer static. The it is actually evaporating. So I wanted to apply information balance, and that's what let's now put forward. So I'll write it down so it's not completely. Okay, so here is another window. There is a surface reaction, so we can remove that as the PS term. And I have already given that. So you want to write the balance of both A and B. Okay, you want to write the balance of both A and B. So let's start with what is the balance of. It's okay. It's not, if it's not natural, don't worry. But we just, I just want to make sure you try this on your own. This is true. Okay, so let's do that, and I can put pole here. So what are the expressions for n d y? What are the expressions for n d y? Let me put pole. Let's just do this. What are the expressions for n d y? Try this out and small here and think about that. Maybe instead of everything yesterday. So this C everywhere is CD naught. So I'll correct this when I upload this. So this is CD naught, not CS. CD naught wow. So this is CD naught VI, CD naught VI, CN minus CD naught VI. Right. So I just give another 15 seconds. Just think of like if I'm not able to do it, we'll do it. Just try. Like so kind of derive it from the formula. All right, I'll close it now. But we're running for the time. All right, so let's take a look. The results are somewhat split. So the correct answer is actually B, and we will derive it now. Then we'll close the lecture after we finish derivation. Again. Okay, so now the flux in the first phase, right? That's the NAY. I hope it's clear. This is the NAY and DY, sorry. Okay, so the NBY. What is the DBI term? So what is the value of concentration in the gas phase? CV naught. Perfect, right? That's CV naught. CV naught DI is the first term. And I'm not, I mean, not in this N is obviously with the Y component. Then what is the flux in the second phase? Zero. Why? Right? So standard ingredient, both of you are absolutely right. It's a pure liquid, right? So there is no concentrated gradient, clearly. It's pure liquid. But why is it no convection? This is the question I asked. Can there be a velocity? Yeah. So basically, and I will, if you can do this at your home in private, the private data documentary will is that if you apply the equation, if you try to apply the equation, you will see that because there's a bottom wall, it cannot be any velocity. The velocity has to be constant throughout because there's a bottom wall, it cannot be velocity. Another question from that, someone asked last time, and I thought it was a very insightful question, that the flux is clear, there is no concentration related to diffusion, but there cannot be any convection either. So it is actually absolutely zero. This term is zero. And what is the concentration? CL. Zero to zero. So this will make it to be NBY. Here in You just one second and then try to close it, like I don't want to go over time. So whether do you think NDI is positive or negative? So this so concentration of Cl will be much greater than the air concentration. I hope you'll all agree. The liquid phase concentration is a pure liquid, right? So whatever concentration is in the liquid will be much higher than the gas. Right? So this term is positive. What do you think about the interface? Would the velocity be positive or negative if it's evaporated? Look at the convention here. It is going down, but y is also going down, right? So y in the downward direction. So it will also be positive. So the flux of the B phase organic interface is negative. Does that make sense? Because the concentration of organic phase is higher at the interface, lower at y equal to 0, it's actually evaporating upwards, right? The y is going down. So if it's evaporating upwards in the gas phase, the flux is negative. Okay, so that's you can check that. Now let's quickly do A and then we'll wrap up the rest of the class. What do you think will be an AY? Okay, so what is AY? And let's quickly stop this. I'll do the poll quickly. That's another 15 seconds. And then we'll go. Oh, okay. Let's see. That's very spread. We have quite a that's quite a solution. The correct answer is actually C. So let's do okay. Let's quickly see how it is. Now NaY, I would say this is AY minus C minus C naught. Right? This is L. So here this is the concentration of A, right? And then flux, is there any flux of A in the pure liquid? No, there is no A. That goes away. And is there any A in the liquid? What is the value concentration of A in the liquid phase? 0. So even if there is a velocity of A in phase, there is a concentration of A that also goes to 0. And note that this is actually positive. So that means that because B is going upwards and A is going down. So maximum concentration of A is actually at the top. And if it's downward, it is the top. Okay. So next part, we already have NaY and By. Because if you want to do this, I encourage you to try to find modal velocity and the mass velocity at home. Start there and then I close out the problem. So I convince you how this problem is. That we will do the next. All right. Thanks a lot. The next makeup lesson is in November, so check your schedule and homework will be posted. All right. Thanks a lot. Have a good weekend, everyone.